right, so today we're going to talk about KSP, or solubility product. And in essence, we've already dealt with this a little bit because if you remember a while back, we studied solubility rules. And solubility rules, if you remember, those were our A, B, C, D rules. If you want to need a refresher, you might want to just take a quick glance at them. But essentially what we used solubility rules for was to be able to write a net ionic equation. So an example that might be if we gave you silver nitrate. Aqueous means that it's dissolved in water, and we put it together with sodium chloride. The end result would be is that the silver and the chloride will hook up, and these two would try to hook up, but they would be soluble, and they would be considered as spectator ions. So what we have is we have the Ag plus ion hook up with the Cl minus ion and form AgCl. We said that this AgCl was insoluble. In other words, it formed a solid when it was in water. And that was true, kinda. What we actually kind of kept from you is that even the most insoluble salts, like AgCl, is not very. It's a solid when we put it into water. They still dissolve just a little bit. So in fact, if we threw AgCl, if I put this over here, if we threw AgCl into water, the grand majority of it would stay as AgCl, a big chunk of AgCl in here. But a little bit of it would form Ag plus and Cl minus. And what would happen is they're going to establish an equilibrium between those two, and that's what we have written here in this equation. The double arrow, of course, does mean that this is an equilibrium. And at the very beginning, as we said, AgCl, silver chloride, will only go this direction at the start because there is going to be none of this. But as the reaction progresses, you're going to get more and more Ag plus and Cl minus, and they're going to reform. Now, the fact that we have an equilibrium going on means that we can write an equilibrium expression. And we sometimes call that the law of mass action. And I've given this little prompt for you here. And if I were to write this, it would be Ag plus times Cl minus. Now, you may be thinking, but wait, what about this? And I want to point out to you this one thing right here. That is a solid, is it not? And solids never make it into our equilibrium expression. The other thing I want to point out to you here is here it says, say, SP here, solubility product. And that is sometimes a little bit confusing because why do we write SP? Now, it's simple enough when we wrote Ka for acid, or Kb for base, or Kw for water equilibrium. But KSP stands for solubility product, and that's because what happens is when we throw AgCl, I wish I hadn't messed that up, we throw AgCl into water, what happens is that whatever leaves that becomes soluble in water. And if you write the equation out, aren't these two things soluble in water? And the solubility product is what gives us our K. That's probably the best way to deal with it. Now, what you should know about solubility is that water, for every single ion, has, especially for ones that are insoluble, has a maximum number of ions that it can have. So for Ag plus and Cl minus, it has a maximum amount that these two can be in water together. Now, if I show you really quickly here, we have I put on the very last page of your notes, we have a solubility diagram here. And if you take a look, and it's maybe a little bit hard to see, but AgCl's, its K value is 1.6 times 10 to the negative 10, which is ridiculously small. Would you agree? 1.6 times 10 to the negative 10. So in essence, times 10 to the negative 10, what that means is that the Ag plus times the Cl minus concentration will only ever equal this, no matter how much of this or how much of this we put in there to start with, which we'll get to in a little bit. Now, how does this work exactly? Well, remember, in every problem, every equilibrium problem, there's only two types of problems. One is, given the K, solve for concentrations, or given the concentrations, solve for K. Now, another way of saying concentrations when we're dealing with solubility or solubility product is we give you, instead of concentrations, we give you solubility. So let's try a problem. So I'm going to give you this problem right here, and I wish I'd done this a little more quickly, but here we go. So here's a problem you can find in your textbook, and it is copper 1 bromide, and they tell you it has a measured solubility of 2.0 times 10 to the negative 4 moles per liter at 25 degrees Celsius. Now, one of the things I want you to be aware of here is that solubility, they can call it either, sometimes they'll call it molar solubility, and that's what we have right here because it's molar. Moles per liter. But often they'll ask you to do the solubility in grams per liter or grams per milliliter, or some other kind of weird unit. So you always have to be careful when they're giving you solubilities that you realize that it's what unit it is in to begin with. In this case, it is moles per liter. So in order to be able to work with this problem, every single time we deal with something, we're gonna have to deal with an equation. So what we have here is we have CuBr, and it is gonna get thrown into water, and when it does, it's gonna form Cu plus and Br minus. I've not been very good with writing in the states of matter, so I'm gonna do that right now. Now, in this particular case right here, if I'm lost and I don't know what to do, I might start by putting my KSP expression over on the side. So would you all be okay with me saying it's Cu plus times Br minus? And they're asking us in this problem for the KSP, so they're asking us to solve for this. So if we can solve for, if we know what these two values are, couldn't we put them in here and solve for KSP? Yeah? So let's take a look at what they give us to begin with, and we're gonna do an ICE problem. Now, what's important about ICE problems is that you never ever have anything here for an initial amount, because we only care about molarities when we're dealing with a problem. When we start off and we throw our CuBr into water, when we first throw it in there, there is going to be no Cu plus, so it's only going to go in one direction. So that means we have 0 of this and 0 of this to begin with. Now, what we're going to do is we're going to lose a certain amount of this CuBr, and that's called the solubility. However much we lose from the original, that's the solubility. So it's also going to form X here and X here. And another way of saying it might be is that our solubility is X, because that's what we're losing. Again, at the end, we don't really care about what we have, although it is this minus X. We're never going to worry about this. But when we have X and X here, and when we plug it back into our equation over here, wouldn't that be X times X is equal to our KSP value? True story? But here's the problem. What is our X? Because if we know what our X is, we can solve for the problem. And up here, we have this value. Do you see how it says 2.0 times 10 to the negative 4? So X is equal to 2.0 times 10 to the negative 4, because X is the solubility, and that is whatever leaves, whatever quantity leaves, that's the solubility of this CuBr. In fact, I probably should have, instead of writing X in here, I should have written 2.0 times 10 to the negative 4 here, and 2.0 times 10 to the negative 4 here. Now, if I plug that in into my equation, 2.0 times 10 to the negative 4 squared, you're going to end up with 4.0 times 10 to the negative 8. Again, there are units there, and those would be moles squared per liter squared, but because we're dealing with a K problem, they don't really require us to ever deal with units, so we're not. So this is a typical problem where they're going to give us the solubility and ask us to solve for the K. Now, that's a pretty straightforward problem, but what if we gave you a slightly more complex problem where it isn't a 1-to-1-to-1 ratio, which, again, happens. So let's do this problem right now, and in this problem, we're going to be dealing with lead 2 iodide. Now, I'm going to write out the equation for this, because in all equations, that would be my starting point. And if you're just trying to figure out what do I do in a problem, that's your starting point always. PbI2 is going to form Pb2 plus, and you have to be really careful here, because here it's going to form 2I minus. Now, for lack of time, I'm not going to put in that this is solid and these are aqueous, although I just wasted the time saying that. But let's take a look at the information they give us. Then they say that by experiment, blardy, blardy, blar, it's found that 1.2 times 10 to the negative 3 moles of lead 2 iodide dissolves in 1 liter of aqueous solution. Whatever dissolves, that's the solubility. So wouldn't 1.2 times 10 to the negative 3 divided by 1 liter, pretty sure that's 1.2 times, I think I'm writing up above where you can't see it, so I'm going to hold this back down. Sorry about that. 1.2 times 10 to the negative 3 molar, that's going to be the solubility. That's how much is leaving this amount here. So if I do an ICE problem, ICE, right? If I do an ICE here, this, we're going to have nothing to start off with here. We're going to have a bunch of this, but it's a solid, so we don't worry about its concentration. And we're going to have 0 and 0 of this. Again, remind yourselves that we have a PbI2 that we are throwing into water, right? And we throw it into water, a certain amount of the Pb2 plus and the I minuses will allow it to be hanging out in here. The K will determine how many ions we're allowed in here. Now, since this is a 1-to-1-to-2 ratio, this is gonna lose X. This is gonna gain X, and isn't this gonna gain 2X? And when we get to our final equilibrium values, we're going to lose X from here, but again, we're not going to be able to work with that. But didn't they tell us that the amount that left, or the solubility, was 1.2 times 10 to the negative 3. That is equal to x. So solubility is equal to always x. So if we know that, then can't we then say here at equilibrium, wouldn't we have 1.2 times 10 to the negative 3, which is, equal to x? And then wouldn't we have here 2 times 1.2 times 10 to the negative 3? Now, if you were just wanting to do a problem, you're like, I don't like putting numbers like that in here. Well, if we wrote our KSB expression, right, which I should have done at the beginning, wouldn't our KSB expression be PB2 plus times I minus squared? And remember, we've gotten away from having to deal with coefficients, so be aware that this 2 comes right here. And when I actually plug in my values, let's pretend that we're not including this or this right now. We're just gonna include the x and the 2x, and then we can plug it in if that makes it easier for you. I'll have x here, and wouldn't that be x times 2x? And if I do the math here, would that not be 4x cubed? And all we have to do then is take our solubility x, which is this right here, and plug it in here. So wouldn't that be 4 times 1.2 times 10 to the negative 3 all cubed? And when you do the math on that, you end up with 6.9 times 10 to the negative 9. And if I wanted to put the units in here, wouldn't it be molarity cubed? Now, if you'd wanted to plug these numbers directly in here, you realize we could have done it like this. We could have said, oh, the PB2 plus at equilibrium is 1.2 times 10 to the negative 3. And the I minus at equilibrium is 2 times that, and that's going to be all put into here, so that would be 4.2 times 10 to the negative 3, and all of that would be squared. So if you wanted to do the math, you could, if you liked. Ooh, that's wrong math. I think it's 4.4, sorry. Math in my head. So these both will get you to the same answer. And it's a little more complex, but I want to point out 2 things to you here. Whenever we have a coefficient like this right here, it's going to impact us in 2 places. 1, it's going to impact us with our x values, and 2, it's going to impact us with how much we in our squaring. Yeah? I was going to say, do you have any questions? But right now, we've just gone from the solubility, our x, to our k. But what if we go the opposite direction? So let's try an opposite direction type problem. So we're going to give you the k, and we're going to ask you to go backwards and solve for the x, or solubility. In fact, can we lock into our heads where it says calculate the solubility? Can you guys in your heads just think that is x? So then let's take a look and see what calcium fluoride looks like, and let's solve together. So if you take a look at the first step, always you should write an equation. So wouldn't that be CaF2, and wouldn't that go, and wouldn't that form Ca2 plus and 2F minus, yeah? Now, if I want to, and I'm gonna get in the habit of doing this, let's put our KSP value right here to begin with. Wouldn't that be Ca2 plus times F minus all squared? Because remember that 2 comes up here. Let's keep that there so we don't make any mistakes here. But now watch what they do. They ask us to solve for the solubility, and they're giving us an initial K value of 3.4 times 10 to the negative 11. I'm gonna put that right here so we have it, times 10 to the negative 11 equals this. So now we're gonna set up and just do an ICE problem like we normally would. Can we get used to the fact that there's nothing gonna be here, right? Initially we have 0 of this and 0 of this. We're going to, for every one of these we lose, don't we gain 1 of these and 2 of these? So wouldn't this be minus x from nothingness, right? Wouldn't this be x, and wouldn't this be 2x? And then here, wouldn't we, actually I shouldn't put this in here, just the change is only x. And then at the bottom, wouldn't we have, I don't know why I'm doing extra lines here, that's just kind of silly. Wouldn't be taking x away from some solid, which it doesn't matter to us, but wouldn't we have x and 2x right here? So if we plug that back into our equation, wouldn't we be plugging x in here and 2x in here? So if you take a look at the math here, isn't this just a matter of gathering like terms? And you're gonna discover this really quickly. That's gonna give us 4x cubed is equal to 3.4 times 10 to the negative 11. By the way, the 10 to the negative 11 kind of indicates how little dissociates and how much stays as a solid. But then couldn't we take the cube root of both sides? And when you do the math and you isolate x, you're gonna get a value for your x of 2.0 times 10 to the negative 4. That is our molar solubility. But there is one step farther here because they didn't ask us to solve for the molar solubility. Look what they asked us to solve for. Then they asked us to solve for the grams per liter, not moles per liter, which is what this is. So then we would have 2.0 times 10 to the negative 4 moles per liter, right? Wouldn't that be our thing? But isn't that moles? Well, couldn't we convert moles into grams by going 1 mole of the CaF2 is equal to the molar mass, which I did not bother to figure out because I did not realize it. I don't have my calculator with me. So we'd have to convert to grams, and all we'd have to do is do a molar mass conversion to get from this 2.0 times 10 to the negative 4 molar as our x to our grams per liter. Now, let me finish off by showing you a couple of things here, and let me recap here. This sheet right here is probably the best comparison I could give you. The solubility product at KSB is just a K value. It tells you essentially how many ions you're allowed in solution. What this means is that if you drop even a speck more of a solid that can be dissolved in water, equilibrium will form with whatever broke apart and whatever you had originally. So if I have a solid in here, right, and the water allows me to have 10 particles of that solid, right? If an 11th particle, one more particle comes in here, now all of a sudden I'm going to end up with an equilibrium going back and forth. And KSP is just another way of saying equilibrium. Solubility, however, is how much of the solid dissolves to get the maximum amount of ions in solution. In other words, solubility is X. So I want you to read through this, and I'm going to give you a few problems to do. Whenever you need to, you can look at this sheet. It's at the back. It's going to give you all of the KSPs you're going to work with. Hopefully this has been helpful. If you need to pause and rewind and look at this other stuff, feel free to do that. Thanks so much. Bye.